Namaskaram. I welcome you all to the beginning of the August event of Karili Svādhyāya. From today onwards, Svādhyāya 1.1 begins. The theme of Svādhyāya 1.1 is finitely generated Abelian groups. Let me introduce you all to our speaker, Dr. Soumya Dey, who is currently an assistant professor of mathematics in the School of Interwoven Arts and Sciences, Kriya University, Sri City. Dr. Soumya Dey has completed his BSc from St. Xavier's, Kolkata, and he has completed his MSc in mathematics from Ramakrishna Mission Vivekananda University. After that, he completed his PhD in mathematics from IISER Mohali. For the next 3 years, he spent as a postdoctoral fellow in IISER Bhopal, CMI Chennai, and IMSc Chennai. And now he is in Kriya University. Soumya Dey has always been an integral part of Kariliv and an active member. He has organized many talks and events. And now let me invite him as a speaker of this event. So over to you, Dr. Soumya Dey. The stage is yours.
Yeah. Thank you, Amlan, for the nice introduction and organizing this to you and Tomogno and Ritoprovo and whoever is associated with the organizing team. So the plan for this event is to basically give some idea about what our abelian groups are. Okay. I hope many of you who are attending this session know what is a group, right? And maybe you also know what is the meaning of abelian group, right? So in today's talk and the following 1 week, the plan is to give you a proof or discuss with you a proof of some theorem called the fundamental theorem of finite abelian groups. Okay, that is the main goal of this event. Yeah, so let us begin. I would like to know from you how many of you have studied some amount of group theory before. Can you raise your hand or something? We do that? Okay. All right. So many of you have seen groups before. That's a good thing. Okay, you may lower your hands now. Thank you. Okay, so you know what is the meaning of a group. So what is a group? You have some set along with some operation, right? Some binary operation. And the properties are, you have this associativity property, and then you have some special element called the identity, such that if you multiply any element with identity, you get the element back. You have something called the inverse of each element. So I give you some element, arbitrary element of the group. There is a unique element in the group. If you multiply these two, you will get back the identity. Okay, that's called the inverse. And now, when do you say such a group is abelian or commutative? Okay, so if for all A, B, two elements in the group, okay, if you have A times B is equal to B times A. Okay, if this happens, we say that this group G dot is abelian. What are some examples of abelian groups? Yeah. If you would like to tell me some examples, you can raise your hand. Or maybe some of you can unmute and say, Yeah, Sahil.
Rational number under addition. Set of all rational number under.
Set of all rational numbers under addition. Very good. So we denote it by Q plus some more. Anyone?
R star under addition, multiplication.
R star. So what is R star? You basically remove 0 from the set of real numbers, and you have the multiplication operation. That is abelian. Very good. Some more.
Integers
Omkar?
under addition.
Sorry.
Integers under addition.
Integers. Yes. Very good. So all these are infinite groups, right? Whatever examples you are giving, some finite groups maybe.
Sir, Z3 with addition modulo 3.
Okay, Z3 or any Zn, right? So any Z mod Nz along with the addition, okay? Mod 3 or mod n addition, right? So this example, so last two examples, okay, Z and Z mod Nz, these are called cyclic groups. Okay. What is the meaning of cyclic group? This means that in each of these groups, you can find at least one element. Okay. If you multiply that element some finite number of times, you can get all other elements. Okay. So you basically can generate the whole group using just one element. Okay. For example, in case of Z, what is that special element? Or at least one, which is 1, right? Or you can take -1 also, right? So why 1 generates Z? Because you give me any other or any integer, say n belonging to Z, right? If you give me, what I can do is I can, so depending on what is n, so namely if n is positive, what I'll do is I'll add 1 n times, right? So if n is bigger than 0, what I'll do is I'll add 1 some n number of times and I'll get n. Okay? In case n is negative, what I'll do is I'll add 1 minus n times. So minus n is positive, right? And what I'll get is, what do we get? Yeah, anyone?
So minus n.
So if n is negative, what do you do? Right. So you get minus n. But I want to write this n as some sum of ones or its inverses, right? So from this, what you can say is n can actually be written as -1 plus -1 and so on, minus n times. Okay. So in this way, for example, for 0 also, you can just add 0 times 1. Okay. So what I mean here is, given any element of Z, you can add 1 or its inverse -1 sufficient number of times to get that n, right? So any natural number can be generated by 1 or -1. Okay. All right. Similarly, for Z mod Nz, okay, you have this element which is basically the class of 1, which we denote by 1 bar, right? And this special element generates the whole group. Okay, I hope you all know this, right? Any element can be written as a sum of ones or 1 bars. So these are called cyclic groups. All right. Now, someone said in the very beginning, one example of an abelian group is K4. Okay. What is this K4? Let me write. So K4, it's called Klein 4 group. Okay. So it has 4 elements. So one of them is the identity. Then you have A, and you have B, and you have C. Okay, there are 4 elements. And so you have to say what are the multiplications, right? So if you multiply A with B, you get C, right? And then if you multiply B with C, you get A. You multiply A times C, you get B. Okay, and the other ways also. So for example, these are actually, so BA is same as C, CB is again A, CA is B. And there are some more relations, right? For example, A times A is identity. Okay, B times B is also identity. C times C is also identity. Okay, so this is the group, how you describe this group. Okay, so there are some more examples of, there are many examples of finite abelian groups. So what is this structure theorem or the fundamental theorem of finite abelian groups telling us? Okay, let me state that theorem. That is our goal for now, right? So the fundamental theorem of finite abelian groups. The statement of this is this, okay? It says that any finite abelian group okay, is a direct product of cyclic groups. Okay, so what is the meaning of direct product? We'll define. Many of you maybe have already seen the definition, but the main idea or the what this theorem is telling us is, you give me any finite abelian group, okay, you can see that group as a product of simpler groups, namely cyclic groups. So cyclic groups are the simplest groups we can imagine, right? You just have one element which generate your whole group. So it's very easy to understand. So cyclic groups are the simplest group you can think of. And what this theorem is telling us is, any finite abelian group can be, expressed as a product of some kind of product of cyclic groups. Okay, so if you understand cyclic groups, you understand finite abelian groups. Okay, that is the idea of, it's one of the most famous or most important theorems in group theory. Okay, so we'll try to understand first the statement and then the proof. Okay, So the only term which we have not discussed here is this direct product. Okay, all other terms you know. You know what is the meaning of a finite abelian group, and you know what are cyclic groups. So let us understand what is the meaning of a direct product. Okay. So I'll write down the definition of a external direct product now. Okay. So let me write down the most general definition, and then we'll see some example to understand that. Okay. So suppose you have say n groups. Okay. So if G1, G2 up to Gn are groups, okay, then the Cartesian product what is the meaning of Cartesian product of sets? Okay, you just take n tuples, all n tuples, right? So you write like this. So G1 cross G2 cross dot 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 Gn. Okay, what is this set? You have basically elements of this form, right? So A1, A2 up to An, right? Where so this is nothing but this set is nothing but all these n tuples such that A1 is from G1, A2 is from G2, and so on. An is from Gn, right? This is the meaning of Cartesian product. So you have this Cartesian product as a set, and we can define an operation on this set. Okay, what is that operation? So let me write. So this Cartesian product along with the operation. What is the operation? So you take two such tuple. Okay. So A1, A2, An, B1, B2, Bn. All right. I want to define how do you multiply two such n tuples. And the most natural way to do it is component wise, right? So this A1 and B1, both of them are elements of G1, right? The first group. So you know how to multiply these two in G1. Okay. So the first element of the product can be A1 times A2. Sorry, A1 times B1. Similarly, the second element could be A2 times B2 because both A2 and B2 are from G2. So you know how to multiply them. So the second element will be, second component will be A2 times B2. And so on. Last element would be An times Bn. Okay. So what I want to say is you start with n groups. You consider the Cartesian product G1 cross G2 cross Gn. Along with this operation, this forms a group. Okay. Okay. And we call this the external direct product of these groups. So of G1, G2 to Gn. Okay. Let us take a quick example. Okay. So suppose you take G1 to be Z mod 2Z. So so Z2, okay, G2 to be Z3. Okay, let's take only two groups. So what is the meaning of Z2 external direct product Z3? Okay, so as a set, this contains all ordered pairs A comma B, where okay, this A is coming from Z2 and B is coming from Z3, right? So there are 6 elements, okay, in Z2 cross Z3, and then you have to say what are the how do you multiply two elements. So let us see some examples. For example, say in Z2 you have two elements. Let us denote as say, identity and A, and Z3 you have 3 elements, identity B, B square. Okay, so let us take one. First element is identity comma identity. Okay, this is there in Z2 cross Z3. You take any other element, for example, say A comma B. If you multiply these two, what do you get? Anyone?
Same as
Yeah.
AB.
E into A.
A comma B, right? Very good. How about A comma B times A comma B? What do you get?
E comma B square.
E B square.
Someone of you saying E comma B square. Why is it? Because A times A is identity, right? A is from Z2, so A times A is identity. So it's E, the first component. And in the second component, you have B times B, which is B square. Very good. So that's how you multiply elements in a direct product or external direct product. Okay, you can try other examples and see. Okay, so that's how you understand a direct product of two cyclic groups. Okay, very good. Now let us come back to the general form. So we have n different groups, G1, G2, Gn. You are considering the external direct product. Okay. Now, for every I in between 1 and n, for 1 less equal to I less equal to n, you can think of some subset. So Gi bar, I'm calling this. Okay. What is this? So it is defined like this. Okay. So what you do is at the ith coordinate, you have elements from capital Gi. Okay. But apart from that, the ith coordinate, all other coordinates, you have identities. Okay. So what I mean is this. So you have, sorry. So you have identity 1, E1. So E1 is the identity of G1, and so on up to EI minus 1. At the ith place, you can vary the element over Gi. So I'm writing G small gi, and again from I plus 1th coordinate, these are identities. Okay. So all these n tuples, and then this Gi is varying over capital Gi. So clearly, this is a subset of the external direct product, right? So Gi is a subset of G1 cross G2 dot 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 up to Gn, right? Because you are collecting some of the n tuples, right? What you can check is this Gi bar for every I, this Gi bar is a subgroup of this external direct product. Okay, so this is the first exercise for you. Okay, so please note down whenever I say exercise, your job would be to discuss this in the following days. Okay, so the exercise is this: your Gi bar, this is a subgroup. Okay, this is how you write subgroup, right? Subgroup of G1 cross G2 dot 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 Gn. Okay, not only that, this is a normal subgroup. Okay, so another exercise. This is not just a subgroup, but a normal subgroup. Okay, this notation means normal subgroup. It's very easy to see. Okay, it's very easy to see. You can check. Okay. Okay, let us see another property of this. So all these are simple exercises. If you consider the map, okay, I'm denoting it by pi I, which is from Gi bar to Gi. Okay, how are you defining this function? So in Gi, you have n tuples, right, where the ith coordinate is varying over capital Gi and all other are fixed at identities. So you take some such n tuple where all these are identities at the ith coordinate, you have Gi. Okay, so you send this element to Gi. Okay, all of you understand this map, right? Okay, so what you have to show is this is an isomorphism. Okay, this map is an isomorphism. Okay, what is the meaning of isomorphism between two groups? Okay, let me recall. So isomorphism means it's a homomorphism, which is
1 1
yeah, it's a homomorphism which is both injective as well as surjective. Okay, that is the meaning of isomorphism. So I'm writing in bracket. This means it's a homomorphism which is also injective as well as surjective. Okay, so you check this. All right. Now you notice one thing, that if I give you any element from this external direct product, G1 cross G2 cross Gn, okay, any element, it will look like this, right? A1, A2 up to AN belonging to G1 cross G2, cross Gn, right? You take any element, you can write this element as a product of other elements. How? So this element A1 to AN, you can write this as, so the first element in the product is, you have A1 in the first coordinate, and all others are identity. So E2 up to En. The second term in the product is, you have E1. The second coordinate is A2. Okay. And then again you have E3 and so on up to En. Okay. And you go this way. Finally, the last element is E1, E2, dot, dot, dot. You have En minus 1 ending at An. Right? So there are n terms in this product. And if you multiply, you know how to multiply elements in this direct product, right? Basically component wise. So you can see the first component, the first coordinate, okay, what it will come? It will come A1 times E1 times dot 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 up to E1. So many n minus 1 many E1s and one A1. If you product, you get A1. Similarly, the second will be, the second coordinate of this product after multiplying would be A2, because you have one A2 in the second term and all others are E2, the identity. Okay. So you understand why this product will give you A1, A2 up to AN. But there is a very nice idea here. This expression is in some sense unique. What do I mean by that? Okay, so you start with any element of G1, G2, Gn, okay, and if you fix a rule that I want to express this as a product of n elements, where the first element will come from, where it is coming from, this element A1, E2 dot En, where it is, in which subgroup it is belonging? Anyone can
G
tell?
bar 1.
U1 bar.
G1.
Very good, very good. So this is in G1 bar, right? Similarly, the second term is in G2 bar, and so on. The last term is from Gn bar, right? So if you fix this rule that you give me one element, any element from G1 cross G2 cross Gn, and you want to express that as a product of n elements, where the first element will come from G1 bar, second element will come from G2 bar, and so on. The last element will come from Gn bar. Then this is the only way you can do that. Right? So this expression is unique in that way. Okay. So I'm going to write down now the abstract form. What I mean is this. Hello? Any questions? Okay. So every element A, if you take from the product G1 cross G2 dot 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 Gn, okay, has a unique representation. Okay, how is this? So A is equal to A1 bar times A2 bar dot 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 AN bar. Okay, with AI coming from GI bar. Okay. Okay. Please check this. This is also an exercise. It's just you just have to go through the map or the expression. Okay, that's it. Now, motivated by this, what you can do is you can define something called the internal direct product of in a group. So what is the meaning? So you treat these GI bars as some normal subgroups in a group, right? So you start with this product G1 cross G2 cross Gn. You think of that as your group. And now you know that these GI bars, okay, these are normal subgroups with the property that any element from the product, if you take, you can write that in a product where the ith term will come from the GI bar, right? So let us write down the definition of an internal direct product. You will understand what I'm saying. Okay, so a group G is said to be the internal direct product of some of its normal subgroups. Okay, say N1, N2 up to Nk, if every element, so every A in G has a unique representation in the form A is equal to A1 dot A2 and AK, where your AI belongs to Ni for every I. Okay, so for I equal to 1 to up to K. Okay, it's exactly, I mean, coming from the idea that we just saw, right? You have a group which is basically the direct product, external direct product of GIs, and you have these GI bars which are normal in that product, right? And with the property that whatever element you pick, that has a unique representation in this form. All right. So if you keep this definition in mind, I'm now going to write down two statements. One is both of them are very easy to see. Okay. So what is the first statement? Okay. Let us say it's a theorem. Okay. Let G be a group with normal subgroups N1, N2, Nk. Okay, you consider the map phi. What is this map phi? Phi is from the external direct product N1 cross N2 dot 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 Nk, and the codomain is your group G. So there is a very natural way of defining such a map. Okay, what you do, you take some n tuple, okay, say A1, A2, AN, okay, where do you send this in the group? What is the most natural way of sending? Anyone? So you have, so all these NIs are subgroups of G, right? And A1 is from N1, A2 is from N2, AN is from NK. So A1, A2, AN, these are elements of G, right?
Sir, A1, A2, N.
You mean the product in the group, right?
Yes, sir. Yes.
Very good. So what you can do is you just send it to A1 dot A2 dot to AN. You can just multiply. These are elements of the group, right? So you can multiply these elements and you get some element of G. So you send this n tuple to that product. Okay. It's a well-defined map, no doubt, right? You can check. And this theorem is telling that this phi is an isomorphism if and only if G is the internal direct product of these NIs. Okay. Let me, yeah. So this is the statement, all of you can see. Let me repeat. Okay. So you have a group G and you know that it has some normal subgroups, N1, N2, Nk. Now, there is a natural map from the external direct product of these NKs, N1, N2, so N1 cross N2 cross up to Nk. Okay, you can form this direct product, external direct product, right? You treat all these N1, N2, Nk as groups, individual groups. So you just consider the Cartesian product of them and you have the multiplication that we defined, right? So N1 cross N2 cross Nk is the direct external direct product and it's a group. On the other side of the map, the codomain, you have G, okay, the original group you started with. And what you can do is you can define, you take some n tuple from this external direct product of NIs, A1, A2, AN, you send that to the product of AIs. Okay. This is a well-defined map. Now, the statement of this theorem is telling us that this map is an isomorphism if and only if the group G is the internal direct product of these NIs. How do you see this? What is the idea of this? Okay. So I'll tell you the idea. I'll not go into writing the proof. Okay. So suppose your G is the internal direct product of these NIs. What is the meaning? Okay, we defined. What is the meaning? Look at the definition. Okay, it says that any element of the group has a unique representation in the form of A1, A2, AK, where A1 is coming from N1, A2 is coming from N2, and so on. AK is coming from NK. Right? Any element you can write like this. Now, Suppose you assume that your group is actually the internal direct product of these NIs, right? I want to prove that this map phi is an isomorphism. Okay. So the homomorphism part is easy. You can just check. Okay. So it will be homomorphism. Why is it 1, 1 and why is it onto? Okay. So let us start with some element from G. I want to prove it's onto. The map is onto. So any element in G should have a pre-image, right? So you start with any element, say small g, okay? Because it's an internal direct product of NIs, this G, small g, has some well-defined unique expression, A1 times A2 times AN, where A1 is coming from the N1, right? A2 is coming from N2, and so on, right? So if I give you some such expression, A1, A2, AN, you know that namely the n tuple which is in front of you, A1 comma A2 comma AN, this n tuple is mapping to that product, right? So there is at least one pre-image. Okay, so it's onto. And because of the uniqueness, okay, because of the uniqueness of your expression, okay, in the definition there is some uniqueness, right? In the definition of internal direct product, from that uniqueness, you cannot have two such expressions, two different expressions for the same element. So no two n tuples can map to same element, and hence the map is 1, 1 also. Okay. So this way you can show that if G is the internal direct product of NIs, your map is isomorphism. And the other way is again easy. Suppose it's an isomorphism. You just use this 1, 1 and onto to show that any element in G has at least one expression and a unique expression. Right? So at least one expression because of onto, and uniqueness because of 1, 1. Okay. So I hope you understood what I'm trying to say. Okay, I just gave a sketch of the proof. I want you to write down the proof. Okay, so it's an exercise. Okay. Now, once you understand the proof of this, you have a very easy corollary of this. Okay. What is the corollary? Okay. Someone is saying me to repeat. All right. So suppose I want to prove that if G is the internal direct product of N1, N2, Nk, the map is an isomorphism. Okay. So what I'll do, first I want to prove that this map is onto. So you take any element from the group G, okay, say small g. So small g, because it's an internal direct product, G is internal direct product, small g has some expression, right? Look at the definition of internal direct product. Any element A can be written like A1 times A2 times AK. So similarly, you have chosen some element G, small g, it has some such expression. Now, once you have such an expression, it should be K, not N. AK, right. Once you have such expression, you know that this n tuple, namely A1, A2, dot AK, this maps by definition to A1 times A2 times dot AK, this element. Right? So you have one pre-image of small g. So the map is onto. Why this is 1, 1? Okay. For that, what you have to show, suppose you have A1, A2, AK and B1, B2, BK, both are mapping to some single element in G. Okay. What does this mean? So this element small g, okay, since it's a image of A1, A2, AK, G is equal to A1 times A2 times AK, right? Again, since B1, B2, BK also maps to small g, okay, the image of this is B1 times B2 times BK. That should also be equal to the element small g. So small g has now two different expressions, where in both this expression, the first element is coming from N1, the second one coming from N2, and so on. So this is violating the definition of internal direct product, right? So it cannot happen. The only way for this to happen is the two n tuples that you started with, they are same. Right? So this is the proof of 1, 1. Okay. And the other way is exactly same. The idea is same. You start with, suppose this phi, the map is isomorphism. Okay. Since this is onto, okay, any element in G has a pre-image. So you start with some small g. There is a pre-image, you know, because this is isomorphism. Let that be A1, A2, AK. A1, comma, A2, comma, AK, the n tuple, K tuple, right? Now that maps to the product A1, A2, AK. So you know that G, the element you have taken, that is equal to this product. Right? So it has one expression like this. And the uniqueness of this expression will come from the 1-1-ness, the injectivity of the map. Okay. So only one way to have this. I hope you understand now. Okay. Let us move on. Now we have a corollary of this. What is that? Let G be a group with two normal subgroups. N1 and N2. Okay. Then G is the internal direct product of N1 N2. If and only if okay, two things are true. One is G is N1 times N2. What is the meaning of this N1 times N2? This means that, so let me write, okay. Suppose you have two groups or two subgroups. Okay, let's see. So N1 dot N2, this means this set. Okay. So all elements of the form, so all G in G, such that G is equal to N1 times N2, where with N1 coming from capital N1, N2 coming from capital N2. Okay, so basically you take any element from N1, you take any element of N2, okay, and you multiply in G, right? because both are subgroups of G, you can multiply them and you do that. So all possible products where first one is coming from N1, second one is coming from N2, that forms a group. Okay, and that is basically the meaning of N1 times N2. Okay, so what I want by this statement is any element of capital G can be written as a product of one element of N1 and one element of N2. That's it. Okay. So I want this, and the intersection of these two just has the identity element. So there is no non-trivial intersection. Okay. This is the corollary. It's very easy to see, just see why. Okay. Once you understand the above theorem, it's very easy to see. Okay. So I'll not go into this, but we'll use this. So keep this in mind. This corollary is very important for us. We'll be using this many times. All right. Let me see the time. We are just 1 hour, right? Okay. Very good. Let us begin the proof now. Okay. So our aim is, as I said, is to see a proof of the fundamental theorem of finite abelian groups. But to prove that, we need a few results in the beginning. Okay. So basically we'll have a lemma to start with, lemma 1, and then we'll have one corollary, which I'm calling corollary 1, and then one lemma 2, which will come, which is actually a very technical lemma. Okay. We'll not see the proof today of lemma 2, but assuming lemma 2, we will see a proof of the fundamental theorem of finite abelian groups. And the proof of lemma 2, this I'll be uploading a video, okay, on Monday, okay, in the evening of Monday, and your job would be to go through that technical lemma, which is lemma 2, and understand that in the next 2 days. Okay. So that is the plan. Let us begin. So what is lemma 1? Okay, I will write down the lemma first. Let us understand the statement. Let G be a finite abelian group okay, of order Mn, okay, of order M times N. So M and N are two natural numbers, okay, any two natural numbers. If you take the product M times N, that is our order of the group. What is the meaning of order of a group? This means the number of elements. Okay. So this is a finite abelian group. You can talk about how many elements there are in the group, and that number of elements is M times N. With the property that this M and N, they are co-prime. Okay. What is the meaning of co-prime? This means the GCD of M and N is 1. So there is no common factor between M and N. Okay. So what are some examples? It can be 2 times 3, 6. Right? It can be 4 times 9. Right? So there are many possibilities of M and N. Right? You just need M and N to be co-prime. All right. What this lemma is saying, suppose you have a group which is finite abelian group of order Mn with GCD Mn equal to 1. You consider these two sets. If M is equal to all x in G such that x to the M is equal to identity and capital N is equal to all x in G such that x to the N is equal to identity. So I'm considering two subsets of the group. Okay. These are actually subgroups of G, we'll see. Okay. What is the first set? All elements in the group, if you take the power M of that element, you get identity. So this means that the order of X, okay, what is the meaning of order of some element? This means the minimum number, okay. If you raise X to that power, it will be identity. So X to the M equal to identity means the order of X divides M, right? So for example, if the order of X is 3, this means X cube is identity. Now, this implies that X to the 6 is also identity, or X to the 12 is also identity, right? So when X to the M is identity, this means that the order of X is dividing, is a factor of M. So in the next set, all elements where X to the N is identity, this means all those elements whose order is dividing N. Okay. So if you take these two sets, what I want to say is then G is equal to M cross N. What is the meaning of M cross N? This is the internal direct product of M and N. So to make sense of this thing, right, this statement, what you need this M and N both to be normal subgroups, right? Then only you can talk about internal direct product, right? Okay. So that is the meaning. So that is the first thing you should check here. Okay, let us see the proof. So why M and N are subgroups? I just want to see whether you are with me. So M and N are subgroups. If you want to try the proof, can you raise your hand? How do you prove this? Say M is a subgroup of G. Any volunteers?
So first we show that it is a non-empty subset of G.
Okay. All right. Why is it non-empty?
So the identity will be there.
All right, very good. Then, how do you show that some, maybe Omkar, you want to try?
So we can use a one-step subgroup test.
Right.
In
So what is
this
that?
test, we have to take two arbitrary element from M.
Say A and
Suppose
B.
A and B, and we have to
Let
show that AB inverse is belongs to that A.
Very good. So what I want to say is A, B inverse belongs to M to show or to prove.
Yes, sir.
How do you prove this?
So we have A and B belongs to M. So by the property of the set M, we can say that A to the power M is equal to E, and B raised to the power M is equal to also E.
Very good. Okay.
And to show A B inverse is in the set M, we have to show A B inverse raised to the power M is equal to also E.
Very good.
So to calculate A B to the power minus 1 to the power M is equal to what? It should be
Right.
E. But to prove
It
that,
should
yes.
be. Very good. The strategy is clear. How do you prove this?
This is equal to A to the power M B inverse to the power M.
Okay. Why? Why is it? Why do you say this is true? So can you write always?
No, sir, we can write it always.
In any group, is it true or you are using something?
So this is
No, sir.
finite.
Huh? Sorry?
If
What
it's
is the problem?
Abelian
Yeah.
one, this
Because it is abelian. Yeah. Right. Right. Sure. So because it is abelian, you can rearrange the terms and keep all the A's in the beginning and all the B inverses in the end, which will make this at A to the M times B inverse to the M. And now you know that A to the M times this is nothing but B to the M inverse. And A to the M, B to the M both are identity. So you get identity. So we have proved that capital M is a subgroup. The exact same proof will work for capital N because the definitions are similar. How do you prove this is a normal subgroup? Why M and N are normal subgroups? Who will say? Omkar, you want to say, or you have raised hand from before?
Sir, how to prove the definition of normal subgroup?
Okay. So what is the meaning of normal subgroup?
A normal subgroup means a subgroup n of a group G is said to be a normal subgroup of G if small g and G inverse is belongs to n. For all G belongs to G, all and n belongs to n.
Right. Right. So suppose you take some element M, small m from capital M, and you consider, say, x m x inverse. What you can say? I want to say that this is there in M, right? But again, this is an abelian group, right? So you can rearrange terms, right? So this is nothing but x times x inverse times M,
Yes, sir.
which is M. Because of abelianness, right? Any subgroup of an abelian group is normal subgroup. So life is very easy here. Okay. So we have proved that M and N are normal subgroups of G. Very good. Now, suppose these M and N both are 1. So M and N both are 1. The most trivial case. Right? In this case, you have nothing to prove, right? If both are 1, the statement follows immediately. What I want to mean is if at least one of them is 1, right? For example, say M equal to 1, okay? At least 1, not and. It should be M1 M equal to 1 or N equal to 1, right? In this case, so if one of them is 1, what is the meaning of this? Suppose M equal to 1. So my M, capital M, will become X belongs to G such that X to the 1 is identity. This is nothing but identity. Right? So M will be the identity subgroup. In that case, the other one, capital N, should be your whole group G. Right? So there is nothing to prove. Okay. So let us consider the case where say M is not 1. Say M is not equal to 1. In this case, what can you say about M? Can M be identity? Capital M be identity subgroup? So I want to say if M is not equal to 1, this implies the capital M is not the identity subgroup. How do you prove this?
Sir, if M is not equals to 1, then there exists some element X such that X to the power M equals to E.
How do you say that? You mean some non-identity element?
Yes, sir.
How do you say that? How do you prove such a thing? Right?
We can use a contradiction here.
Contradiction. Okay, what is the contradiction? Tell me.
So suppose our claim is not true, so M is equal to singleton set D.
Okay.
So if M is equal to singleton set D, then all the elements of M raised to the power some power M is equal to E.
Right.
But we can say that E to the power 1 also is equal to E.
Okay.
So M here in this case M can be 1. So.
Is it all others agree with this proof? Okay. Let me give some other proof. Okay. So I want to show that this M is not identity. Okay. So I want to say that at least one non-identity element is there. So if to start with this natural number M, which is not 1, okay, any such natural number has a prime divisor, right? Do you agree with me? If you take some natural number which is not 1, so at least 2, okay, that number has a prime divisor, right? So let P be such a prime divisor, okay? So P be a prime such that P divides M. All right. Now we know mod G is equal to M times N. That is given to us. And P divides M. This implies that P divides mod G. Okay. Now, you must have, many of you have seen this theorem called Cauchy's theorem. Okay. What is Cauchy's theorem? Cauchy's theorem says that if you have some prime dividing the order of a group, there is an element of that order. Okay. So Cauchy's theorem will imply that there exists some G in G such that order of G is equal to that prime P. Okay. But then this implies what? This implies G to the M, which is basically G to the power P to the power M by P. I can just write like this, okay, which is equal to identity. Right? And what is this meaning? This means that G belongs to M. So we have found some element G, and remember that this G is not the identity, right? Because the order of G is a prime number, it cannot be identity. So we have found some non-identity element in capital M, right? So this proves that our M is not the identity element, just the identity. There are some, at least one more non-identity element in capital M. Exactly similarly, what you can say, okay, in case N is not 1, our N, capital N, is not the trivial group. Okay. Now what? So we have, in the case of at least one of them to be not 1, or in case both of them or at least one of them is 1, we know this is not a case to be considered. It's the trivial case. Suppose both of them are not 1, and they are, by this we have found that there are some non-trivial elements in both, right? In this case, what you can do is you note that if you take the intersection of M and N, this is in both, right? M as well as in N. So this is a subgroup of both M and N, the intersection. And there is this theorem called the Lagrange theorem. What is Lagrange's theorem telling us? That if you have a subgroup of a group, the order of the subgroup divides the order of the group, right? So what you can say here, since M intersection N is a subset or subgroup of capital M, okay, what you can say, the order of M intersection N divides the order of M, okay, and the order of M intersection N also divides the order of N. Okay. From this two, what you can say?
That order of M intersection N is 1
Why?
because GCD of M and N is 1.
Exactly. Okay. So you check this line. So from here, what you can say is order of M intersection N is 1. And from here, you can say that intersection of M and N is the trivial group. This is because GCD of Mn is 1. Okay. So please check this line. Why this is true. So what we have shown is one part of the definition of the internal direct product. Okay, namely, so let us see review the corollary that we have seen before. Okay, what is that corollary? The corollary was this. So to show that some group is an internal direct product of two normal subgroups, we need to prove two things. One is the intersection of N1 and N2 is the trivial group, and G is equal to N1 times N2. Okay, if we can prove these two, this proves that our group is actually the internal direct product of the two such normal subgroups. So one of the properties we have shown, namely M intersection N, is the identity. The only thing remaining is that G is equal to M times N. That we will do now. Okay. Note that GCD of Mn is 1 by the assumption, which will imply, I hope some of or most of you have seen this before. What you can do is you can find two integers R and S, okay, such that you can write R times M plus S times N is equal to 1. Because the GCD of M and N is 1, you can do this. Okay. And then what I want to see that G is equal to Mn. So this is what we are proving now. G is equal to Mn. Okay. What is the meaning of this? You take any element from capital G, let A be any element in capital G. Okay, this is what we are proving to prove. Okay, so to prove this, to prove this, you start with any element from capital G, say small a, and you just write A as a product of two elements, the first one coming from capital M, second one coming from capital N. That's it. So what I can do is, I'll write A is equal to A to the 1. Okay. And now we know 1 is equal to Sn plus Rm, right? So I'll write down this is Sn plus Rm, but this is equal to A to the Sn times A to the Rm. Okay. Now, it's easy to see that A to the Sn is an element of capital M. Why? Because is this to the power small m? So note, if you take mth power of A to the Sn, this is basically A to the S whole to the Mn, and Mn is the order of the group. Right? So any element, if you take the order as, the power as the order of the group, you get identity, right? So this is equal to identity because Mn is the order of the whole group G that you started with. So A to the Sn, when raised to the power m, you get identity. This is precisely the definition of m, right? So this means A to the Sn belongs to capital M. And similarly, A to the Rm, if you raise to the power n, exactly same way, A to the R whole to the Mn, again it is identity. This will prove A to the Rm is in N. Okay, so you have found an expression of A, okay, which is A to the Sn times A to the Rm, where this first one is from M, second one is from N, and hence this proves G is equal to Mn. Okay, this is the end of proof. Okay, yeah, so this is, of course, these are technical lemmas, so you can of course go through this. This video will be uploaded soon on one of a Curryleaf website or the YouTube channel. You can go through that and revise this. Yeah, what is the note? Okay, note is this, right? So you start with any element A, small a in G, right? And since we have M and N to be co-prime, I can write this line. Rm plus Sn is equal to 1 for some R and S. And then I just put that value of 1 here. So you start with any A in G, right? You write A as A to the 1. And then in place of 1, I'm writing Sn plus Rm. And you just break it, A to the Sn times A to the Rm. The note is this. You take the first one from the product, A to the Sn. If you raise to the power m, okay, what do you get? A to the S to the Mn, right? So A to the S is some element in a group. You take the power of the order of the group, okay? That is always identity, okay? So if you have some element whose power, mth power is identity, you can say that element is in capital M. Right? Similarly, A to the Rm to the power n is identity, and hence A to the Rm, the second term also in the product, that is in capital N. Right? So you get this expression where the first term is coming from capital M, second term is coming from capital N. So you can write any element of capital G as some element of capital M times some element of capital N, and hence G is equal to Mn. Okay. All right. Very good. We are at 6 p.m. So we have half an hour more. Let us do quickly, okay? We'll rush through now because we don't have much time. We'll now see a proof of corollary 1. What is corollary 1? Let's see. Let us see the statement. The statement is this. Let G be a finite abelian group let P be a prime such that P divides the order of G, then the group G is internal direct product of P and T. Okay, two subgroups P and T for some subgroups P and T of G such that there are two properties. One is the order of P is a power of P, small p, the prime. Okay. Small p to the m for some m. And this prime p is not a factor of the other order of T. Okay. So we have two subgroups, right? Okay. So I want to say that you start with a group G, which is finite abelian, and you take any prime which is a divisor of the order of G. What you can do is you can write G as capital P cross capital T. Okay, so capital P and capital T, these are two normal subgroups of my group G. Okay, such that the order of the first group, capital P, is some power of this prime P. Okay, and the order of the other group T has no factor as P. So P does not divide mod T, the order of T. Okay. So this is the statement. So you can find such a product expression for G. All right. Let us see the proof. So we define what is capital P and what is capital T, right? Let us define. So P, I'll define like this: all x in G such that when you take x to the P to the N, okay, this should be equal to identity. I'll say what is this P to the power N, okay, where mod G is equal to P to the N times K with P not dividing K. So I'm writing the order of my group G as a product, okay, where the first one is some power of P and the next term has no P in it. Okay, so K doesn't have P as a factor. So you put all factors of P in one side, namely P to the something, and you have a P free number, which is K. You can always do that, right? You can always do that. Given any number and any prime which is dividing that number, you collect the maximum possible power of that prime and then times the remaining whatever is left, right? So that's what we are doing here. So you have mod G equal to P to the power n times K, where P doesn't divide K. And you consider the set capital P, which is set of all elements X in G, such that X to the P to the n is identity. And now, what is the other set T? That's basically X belongs to G, such that X to the K is identity. Okay. So I have defined P and T. What are P and T's? And by applying the previous theorem that we just stated, okay, where we had M and N, capital M and capital N, okay, you just apply that. What you get is G is actually P cross T. But then we have to see the properties. You have to prove those, right? So it's easy to see by lemma 1. Okay, G is P cross T. But whether P and T satisfy this property, namely, what are the two properties? First property is capital P, the order of that is some power of P. Okay, that's first thing. And the prime small p does not divide the order of capital T. Okay, let us see how do you prove these two. Okay, let G be any element in P. Okay, for any such element, what you can say by the definition, G to the P to the N is identity. Right? Okay, now you note that when you have in general, okay, in general, you check this. If you have any group G and you take any element X, okay, okay, and you suppose know that X to the power say L, some power of X is identity, right? You can say from here the order of X divides L, right? You can do that. Now you use this. Since you have G to the P to the N is equal to identity, what you can say about order of G? Okay, this implies order of G divides P to the N. Okay, what is the meaning? So P to the power N, what are all divisors of that? It can only be some power of P, right? No other possibility. Either 1 or any power of some power of P. This is only possibility. So from here, what you can say is order of G is P to the R for some R, right? R can be 0. Okay. All right. Now, since every element of P has order, a power of P, right? From this that we got, right? So what we can say, so since every element of P has order, a power of P, you apply Cauchy's theorem. What you can say? what can you say about the divisors of mod P? So you have this capital P. Okay. What can you say from Cauchy's theorem about the order of capital P? Can it have some factor which is some other prime other than small p? What is Cauchy's theorem? Cauchy's theorem is saying that if some prime divides the order of a group, you have some element of that order, that prime order, right? So suppose you have some divisor, prime divisor of mod capital P other than this small p. Apart from this prime, you have some other prime q which divides mod p. Okay. So suppose you have some q which is not p, and q divides the order of the subgroup capital P. What happens? By Cauchy's theorem, you will have some element whose order will be q. But here we are saying all element of capital P has order which is p to the r. We just proved. Right? You took any g from P, and for that g you said, and we said that order of g is p to the r. So any element of capital P, if you take the order, that's some power of small p. Right? Okay. So this says that capital P, the order of capital P, doesn't have any divisor other than small p. Okay, that's the observation here. So mod of capital P is not divisible by any prime other than P. What does this say? This says, what can you say about this number?
This is of the form p to the power odd.
P to the power m, right? Yeah, exactly. That is what we wanted, right? The statement says the order of P should be P to the m for some m. So we have proved one property. Let us see the other one. So for mod T, the order of capital T, what we can say about that? Okay. So what we are trying to prove about mod T, that P does not divide that. Right? The prime P does not divide mod of capital T. We want to prove that. So suppose otherwise, okay. So if P divides capital T, what will happen? If small p divides mod T, okay, you again apply Cauchy's theorem. You can say that there is some y in capital T such that order of y is small p, but that will mean y to the p is identity. Okay. But now this y you are taking from capital T, right? So Y is in capital T implies by definition of capital T, Y to the K, that is identity. Look at how we defined, right? Our definition of T was this. All X in G such that X to the K is identity. Okay. So, since this Y that you have got, that is from capital T, Y to the K is also identity. Now you look at this two statements, Y to the P is identity and Y to the K is identity. Okay. What do you know? You know the GCD of P and K
Doesn't
is
work.
1. Right, right. So GCD of P, small p and small k is 1. This implies you have some S and R. There exists some SR in Z such that 1 can be written as PS plus KR. Exactly similarly as before, you put y equal to y to the 1, which is PS plus KR, which is y to the p whole to the s times y to the k whole to the r. But then you know these two are identity, right? So it is identity. So what you are proving here is y is equal to identity. But that's not possible because order of y is a prime. So y cannot be identity, right? So it's a contradiction. And this contradiction tells us that our assumption was wrong, and hence P does not divide mod. Hence we are done. Okay. This is the end of proof of corollary 1. And in the remaining few minutes, I'll tell you how to apply these. So before that, I'll state what is lemma 2. Again, we'll not prove lemma 2 in this talk, but I'll be giving a proof of lemma 2 as a recorded video, and this will be uploaded on Monday evening. So you go through that, okay? And now we'll assume lemma 2, the statement of lemma 2, and try to prove the fundamental theorem. Okay, let us do that quickly. So what is lemma 2, the statement? Okay. So again, let G be an abelian group of order P to the n for some prime. P. Okay. So we are concentrating our attention to a group which is an abelian group whose order is a prime power. Okay. Sorry. Let A belongs to G be an element having the maximum possible power as the order, maximum possible order. Okay. Among all elements in G. So what is the meaning? You have a group, you look at all possible orders of elements, okay, and you take some element whose order is a maximum possible. Okay, so A is some such element whose order is maximum possible order in the group. Okay. Now what this statement is saying is you consider the cyclic subgroup generated by capital this small a. Okay, so suppose capital A is the cyclic subgroup generated by this element that you have chosen. Okay, okay, then G is equal to A cross Q. Q is some subgroup. For some subgroup Q of G. Okay, so let us understand this. You have a group G, which is abelian of order P to the n. You take some element of maximum possible order. You take the cyclic subgroup generated by that element inside your group. You name that capital A. What you are saying is G is actually an internal direct product of A along with some other subgroup. Okay, that is the statement. Okay, so A, the specialty about A is it's a cyclic subgroup, right? So you can write G as a cyclic subgroup product with something else. So we are going to use this. Okay, it's very important for our proof. Yeah, this is internal direct product. Yes. All right. Okay. So we'll not prove this now. We'll assume this and try to see a proof of the fundamental theorem. Let us see the fundamental theorem. Okay. So this theorem is again this: any finite abelian group is a direct product of cyclic subgroups. Okay, so this is the statement. So I start with some finite abelian group G, and I give you a recipe to express G as a direct product of some of its cyclic subgroups. How we can do that? So this proof will be by induction. Okay, and induction on the order of the group mod G. Okay, so the proof is by induction on the order of G. So what is the base case? The base case is simple: mod G equal to 1. Okay, if it's the trivial group anyway, so the group is equal to the cyclic subgroup generally. So the base case is done, right? So if mod G is equal to 1, easy. Okay, now we suppose that the statement is true for all groups of order at most m minus 1. Okay, so we suppose that the statement is true for all finite abelian groups of order less than m. So up to m minus 1, it is true. All right. Now we want to prove it for a group whose order is m. Okay. So you start with the group. Let G be a group or finite abelian group. Abelian group, right, of order, sorry, group such that mod G is M. Fine. Now, suppose you have a prime P which divides this order M. Okay. So let P is a prime which divides M. By corollary 1, what you can say is G is equal to P cross T, right? Where the order of P is some power of prime, right? That's what corollary 1 is telling us. Okay. So you can write G as some group whose order is some power of prime, direct product with some T. Now you apply lemma 2. What is lemma 2 is telling? Lemma 2 is telling something about the first component, first group, capital P. Because capital P is a group of order prime power, what this says is you can write P as A1 cross A2 cross AK, where all these AIs are cyclic. Why? Why is it true? Yeah. Anyone? How can you say using lemma 2? So P is a group whose order is P to the N, some prime power. Okay. How can you say that P is A1 cross A2 cross AK where all these AIs are cyclic? You look at the lemma 2 statement. Yeah. How do you use this to say that? So lemma 2 is saying what? You have some group, Abelian group of some prime power order. You can write G as some cyclic group cross some other group, right? And you got this A as it's a cyclic group generated by the some element whose order is the maximum possible there, right? So you start like this. Okay, you have G, which is the order of that is some P to the N or P to the R, whatever. At the first step, you can have one cyclic subgroup times Q. You can write G as. Now you look at this Q. On this Q, you can again apply lemma 2, right? So Q can be written again as some A2 cross some Q prime, where A2 is again cyclic. And you do the same thing. So in Q, you find the maximum possible order. You have one element, such element, and you take the cyclic subgroup generated by that element, and you apply this lemma 2 to get Q is equal to some cyclic subgroup times whatever is remaining, some Q prime, right? And you do that again and again. In finite number of steps, you have to stop. This is a finite group, right? So at some point, you have to stop. And what you get is this G is a product of cyclic subgroups. All right. So that's how you use this lemma 2 in this step. Okay. So by lemma 2, what you can say is this capital P that you got, since it's a prime power order group, right? you can write P as A1 cross A2 cross dot dot AK, where all these AIs are cyclic. Okay? And then what you do is you have to do something with the capital T now. Okay? Now, what is the order of capital T? That's definitely less than M. Why? Because this P has at least two elements, right? Capital P, we have seen that, right? You can see this because P is a prime, at least one element will be there, right? So you do the math, and what you get is mod T, the order of T is less than M. And it's again a finite abelian group. So you use induction hypothesis. Since the order of that is less than M, and you have assumed for any such group, finite abelian group of order less than equal to M minus 1, the statement is true. Namely, you can write this T as a product of cyclic groups, right? Cyclic subgroups. What you can say is T is such a product. T1 cross T2 cross, say, some TQ, where all these are cyclic subgroups, where TIs are cyclic subgroups. Sorry. Okay. So finally, what you get, you have G, which is P cross T, and P has this expression A1 up to AK, and T has this expression T1 to TQ. And notice that all of them are cyclic. AIs and TIs, all of them are cyclic. So finally, you have some such expression where this is a product of cyclic subgroups. Okay, so this is the end of proof. What I'll do is I'll record a video for the proof of lemma 2, and we'll upload on the channel of Curry Leaf. You go through. So before I upload that on Monday evening, I want you to go through the proof. Whatever we have done today, it's a lot of things, right? You can assume that it's, you can see, right? So you go through all the steps and be ready for the proof of lemma 2 by Monday evening. Once we upload, you go through that, and then we'll organize some session where we discuss. If you have some doubts, we'll discuss there. Okay, the strategy of the proof should be clear to you, what exactly we're trying to do, and then go through the details. All right. Okay, so we can stop here today.